When I think about osmolarity, I think of a waterfall because osmolarity is based off concentration. I think of the volume of the solute being like the water and the particle being the amount of the solute that is being added onto the water. Once a particle is broken into a solution, I think of sodium chloride or sodium chloride ions, where sodium and chloride break apart because of their charge and we get twice as many osmoles. The water in between the mountains is like the inside of the cell, and the outside of the cell is represented as the ocean. I can say that osmolarity is based off concentration of the particle in a solution, and the higher the amount of the particle, the higher the amount of osmolarity. In this drawing, I have two particles that are being represented, which are glucose, shown as the grapes, and sodium, which is shown as the bananas. And sodium and glucose have a higher concentration on the outside of the cell, which in this case would make the outside have a higher concentration, meaning that there is a higher osmolarity on the outside of the cell. And osmosis is the process of water diffusion, and I drew a waterfall in which I think of osmosis because water will diffuse towards regions that have a higher particle concentration. In this case, we have a higher osmolarity on the outside of the cell, which would make water diffuse towards that region because it loves high osmolarity, which can be described as the water falling down the waterfall to reach the outside of the cell. We have polar particles, which are usually particles that cannot get across the cell membrane because of their size and having a charge. In other words, polar things only like polar things. I represent glucose, shown as the grapes, and the sodium, shown as the bananas, which both are polar particles that cannot get through the cell membrane. But glucose is big in size, and it can only get through the cell membrane through glue. And we know that sodium has a net charge, and it cannot get across the cell membrane. Glucose is part of the polar group, and it is not able to get across the cell membrane on its own because it needs a helper that will get glucose through the cell membrane. Glue is a very important transporter because it helps glucose get through the cell membrane. Glue helps a polar particle get through. I represent glue as the seahorse that likes grapes a lot. And we know that the grapes represent glucose. And what the seahorse wants to do is take the grapes with him everywhere he goes. I show the seahorse is grabbing a grape and it is trying to get glucose to the other side, which is just trying to get glucose to get through the cell membrane. We know that diffusion will always diffuse from higher concentrations to regions that have a lower concentration until it reaches equilibrium, which means equal concentration of particle concentration, just like osmosis, in which water will diffuse to regions that have a higher osmolarity and will eventually reach an osmotic equilibrium. I represent how the seahorse allows glucose to get through the cell membrane and will eventually allow glucose to get into the cell. In this case, glucose is the only particle that can get through the cell membrane with the help of glue. We know that to calculate tonicity of a solution, we need to know two main factors, which are whether or not a particle is able to cross the cell membrane, and it also depends on the osmolarity. Since glucose is able to get through the cell membrane with the help of glue, and we know that sodium is unable to cross the cell membrane because it has a charge and it is polar. The outside of the cell has an osmolarity of 0.4, and the inside has an osmolarity of 0.3. Let's say that glucose isn't able to get through the cell membrane, and the outside would have a higher osmolarity. And we know that water tends to flow to regions that have a higher osmolarity, which would make the cell lose water, making the solution hypertonic. But since glucose has a transporter that will allow it to get through, and let's say that out of the osmolarity 0.4, only 0.1 is glucose and the rest is sodium. The osmolarity on the inside will then increase by 0.1, which would make the 0.4 on the outside decrease to 0.3 because sodium cannot get through. We know that the inside now has a higher osmolarity and will cause the cells to gain water, making the solution hypotonic. An important factor is that when glucose is added to plasma, it will completely diffuse into the cells, meaning that the osmolarity of glucose will be 0 and we will have an isotonic solution, where cells will either gain or lose water. And we know that the normal osmolarity of a cell is 0.3. To calculate tonicity, we need to know two very important factors, which are osmolarity, and we know that water will move to regions that have a higher osmolarity, and two is to know whether or not a particle is able to cross the cell membrane or not. And we know that the outside of the cell has a higher osmolarity because it is at 0.4, and water tends to flow to regions that have a higher osmolarity, which would make the cell lose water and make the solution hypotonic. But since glucose has a transporter that will allow it to get through, let's say that out of the osmolarity of 0.4, only 0.1 is glucose and the rest is sodium, the osmolarity on the inside will then increase by 0.1, which would make the 0.4 on the outside of the cell become 0.3 because sodium is unable to get through the cell membrane. We know that the inside now has a higher osmolarity and will cause the cells to gain water, making the solution hypotonic. But when glucose is added to plasma, it will completely diffuse into the cell, which would cause glucose osmolarity to be 0, meaning that now we have an isotonic solution due to having an osmolarity of 0.3 inside and outside the cell. Here I drew 3 jellyfish, which each represent a cell. For one of the jellyfish, I drew 3 starberries, which represent the 0.9 of sodium chloride. And this solution, we know that the inside of the cell, it has an osmolarity of 0.3, and 0.9 sodium chloride solution has an osmolarity of 0.3. So this means that the jellyfish or the cell won't gain or lose water, making, the jellyfish look happy. For the second jellyfish, I drew blueberries, which represent the 5% dextrose. And dextrose can also be called glucose. And since it's able to get in with the help of glue, all that 5% dextrose will diffuse into the cell and metabolize the outside of the cell to have an osmolarity of 0, and the inside will stay at 0.3. And we know that water goes to regions of higher osmolarity, causing the cell to gain water, and this would make the solution hypotonic. And this causes the jellyfish or the cell to gain water, and it looks like it's about to burst or explode from having too much water. For the last jellyfish, I drew cherries, which represent the 0.9 sodium chloride, and the blueberries represent the 3.3 dextrose, and we know that dextrose is also known as glucose, and glucose is able to get through the cell membrane by glue. Let's say that 3.3 dextrose is 2/3 of 5% dextrose, which makes it have an osmolarity of 0.2. And 0.9 sodium chloride solution has an osmolarity of 0.3. Since dextrose is able to get through, it will completely diffuse into the cells and it will metabolize, making the osmolarity be 0, and leaving the outside and inside of the cell have the same osmolarity, making the solution isotonic.